Hey everybody, welcome back. So as promised, we're going to now talk about the electromagnetic spectrum. So we said last time that a wave travels at a speed that equals its wavelength times its frequency. So if we consider a light wave, an electromagnetic wave, traveling in free space, we know that it travels at this special speed, c, 3 times 10 to the 8 meters per second. So what we can do is say, well, that speed has to equal the wavelength of the wave times its frequency. Now you'll notice that I put a little subscript O here, and I'll usually read that as lambda naught, N-A-U-G-H-T. That's common in physics. If the subscript is a 0, you say a naught. So lambda naught is known as the free space wavelength of the light wave. And it's an important quantity because the wavelength of the light, as we'll find out, depends on what medium the light is traveling in. So if light is traveling in water, that light wave will have a different wavelength than if it's traveling in air. The frequency of the light, that light wave, is always the same for that particular light wave. So the frequency is conserved. It's the same as the light goes into different materials, but the wavelength and the speed will change. So lambda naught is known as the free space wavelength. Now, we find out in nature when we look that we see light waves, electromagnetic waves, with all sorts of frequencies, from very small frequencies to very large frequencies. So we love to categorize things when we do science. So the different frequencies have been categorized into different ranges, and that forms what's called the electromagnetic spectrum. So let's talk about that. And you should be familiar with the spectrum. Most of our focus is going to be on the visible portion of the spectrum, the part of the spectrum that we can see, our eyes are sensitive to. But here is a breakdown of the electromagnetic spectrum. And again, because the frequency of a wave doesn't change as the light goes into different materials, it's the frequency that's going to determine what part of the spectrum the light wave belongs. You could also, though, categorize it by the free space wavelength. So that's the special wavelength of the light if it's traveling in free space. Okay, so let's just go through the different portions. And this table is listed from low frequency to high frequency. Now there's a inversely proportional relationship. So a high frequency means that's going to be a long wavelength because the speed, right, is wavelength times frequency. So if the frequency goes up, that means the wavelength will go down for that particular light wave in that material. So these radio waves are going to be the lowest frequency waves, which means they're going to have the longest free space wavelengths. And guys, look, these limits that I have here, these ranges, these are not sharp edges. So these are approximate values. So radio waves are going to have frequencies that are typically lower than 300 megahertz. If you remember our metric prefixes, capital M is mega, which means million. So that means free space wavelengths are greater than about a meter. So radio waves, that's where you're going to find some common examples, AM, FM radio, and TV. So TV signals, not cable TV, but TV signals that travel over the air or through the air. Like you may have a TV antenna to get local TV. That's going to be in a radio portion of the spectrum. And these can be easily broadcast by having charges moving back and forth in antennas. Okay, if we go up in frequency from about 1 billion to 3 times 10 to the 11 hertz or cycles per second, so those are free space wavelengths from about 30 centimeters down to about 1 millimeter. So I have these ranges going from the longest wavelength to the shortest wavelength. That's the microwave portion of the spectrum. So you've heard of microwaves, I'm sure, with microwave ovens. those use higher frequency microwaves to heat your food and cook it. But another big use of microwaves are cell phones. So cell phones actually use lower frequency microwaves to broadcast their signals. And fortunately, right, we cannot see microwaves or radio waves, because you imagine, right, if we could actually see that radiation, respond to that, my gosh, it'd be hard to see anything, right, other than that radiation. Okay, if we go up in frequency from about, I should mention also that microwaves can also be produced by oscillating electrons, although it's a little bit trickier than in a conventional antenna that would broadcast radio waves. All right, so now we go in the next portion, the IR or infrared, about 3 times 10 to the 11 to 3.8 times 10 to the 14 hertz. Wavelengths, free space wavelengths, from about a millimeter down to about 780 billionths of a meter, or nanometers. And that's the IR or infrared portion. Now, again, our eyes, the cells on our retinas are not sensitive to these values, these frequencies. Certain animals, like pit vipers, snakes that have special infrared cells in those pits on their face, they can actually see or sense, I don't know if see is the correct verb, but sense infrared radiation. Now, the infrared, there's a lot of infrared radiation coming from what we would think of as typical heat sources. So like an incandescent light bulb will produce a lot of infrared radiation, or objects that have surface temperatures that are, typical temperatures, like your skin, for instance. If the surface temperature of your skin can be, around 80, 90 degrees or so, the atoms and molecules on your skin are actually moving back and forth, and they're actually producing infrared radiation. Now, again, our eyes aren't sensitive to that, but as you probably know, if you watch cop shows or whatever, there are special infrared detectors or goggles that you can put on that are sensitive to that radiation, so you can see people, the infrared radiation coming off of the people. Okay, so that's infrared. To produce infrared radiation just by moving electrons back and forth, that's tricky. These frequencies are much too high, in fact. But there are ways we can get electrons to make those transitions in atoms or molecules or in structures. Remember, we talked about the 2 ways that light can be emitted. So there are structures where we can engineer them and have them emit infrared radiation. A great example is an infrared light-emitting diode, or LED. So if you have a TV remote, your TV remote is actually sending flashes of infrared radiation or light to the detector on your TV, and that's how it communicates with it, through that infrared LED. Also, we use what are called semiconductor lasers to send infrared light through optical fibers to communicate. Okay, now we get to, I guess, maybe, I don't know if it's our favorite, but the part of the spectrum we can see with our eyes, if you have healthy eyes, and that would be the visible portion of the spectrum. So these frequencies are, just think of that. The electric and magnetic fields are oscillating between around 4 to 8 times 10 to the 14 times a second. That's incredible, right? And the cells on your retina, the photoreceptors, the rods and cones, actually pick up that oscillation, and that electromagnetic field wave drives creates an electrical response in your cells at those frequencies. So in terms of free space wavelength, about 780 nanometers down to about 390 nanometers. Okay? Now I'm going to come back and talk more about the visible spectrum, since that's the part we can see. But let me keep going here. If we go up in frequency, down in free space wavelength, now we're in the ultraviolet or UV part of the spectrum. The biggest natural source of UV radiation is, yes, our sun. Okay, we can also engineer and have make ultraviolet sources. I mentioned infrared radiation coming from electron transitions of energy transitions between levels. The same would be true for visible and ultraviolet. So these frequencies are so high that this is not just a conventional antenna transmission like in a radio wave. We have to do some other engineering and have transitions between energy levels. But we can make ultraviolet sources. And as you may know, ultraviolet sources can kill certain viruses and bacteria. So they can be handy in medical fields. Okay, also, I'm sure you know that ultraviolet radiation from the sun can also damage our cells, skin cells. So we have to be careful there. If we go up in frequency, down in free space wavelength, now we enter the X-ray portion of the spectrum. These frequencies are super high. I know that's not very quantitative, but very high, and the wavelengths are extremely short. I went ahead and chose to use the angstrom, just so you see it being used here. Remember, an angstrom is 10 to the minus 10 meters. So from about 100 angstroms down to 0.001 angstroms. I could have used nanometers, right? But I chose to use angstroms. Now, X-rays, there are naturally occurring sources of X-rays in space, I should say. Our sun also produces some X-rays. But we can also artificially produce X-rays, of course, because everybody's heard of getting your X-ray done, right, in an X-ray machine. So this radiation is so high frequency that it penetrates very easily soft tissues. It doesn't go quite as well through denser tissues like bone, so we can take X-rays of people and see your skeletal structure. So X-rays, to produce X-rays takes some doing. It does involve accelerating electrons, but it has to be done in a special way in an X-ray tube. Okay, now, the highest frequency portion of the spectrum, that's called the gamma ray portion of the spectrum, but this is sort of a special part of the spectrum. In fact, you'll notice that there's some overlap. Gamma rays greater than about 3 times 10 to the 18 hertz, well, that looks like that puts it in the X-ray portion. But gamma rays are special because they're coming from special interactions. They're either coming from radioactive nuclei that are decaying and spitting out gamma radiations, this high-frequency electromagnetic wave, or there's another basic phenomenon that can happen where matter is converted to pure energy in what's called a parannihilation. Well, that's one example, parannihilation, where matter and antimatter can combine and give a gamma ray burst. I think I talk more about that in the special relativity part, I believe. But so that can happen in nature. But again, gamma rays are coming from special sources. Nuclear decay or matter to energy conversion in something like a parannihilation process. Now, there is an abundance of gamma radiation going right through you now, in fact. So there's a lot of background gamma radiation coming from nuclear decays and from matter to energy conversions. Gamma rays, because they're so high frequency and they're pure energy, they're sort of hard to absorb and stop. I mean, you can absorb gamma radiation if you have a dense enough material and enough material. But so there's nothing to fear with gamma rays unless you get a huge exposure of gamma rays at one time. So they are naturally occurring, and like I said, there's a constant gamma background radiation, and gamma rays are zipping right through you now. Okay, so that's the part of that is the electromagnetic spectrum. You should be familiar with it. What I want to do now, though, is concentrate on the visible. So if we look in the visible, we see that different frequencies in the visible portion of the spectrum appear different colors to our eyes. So this forms the rainbow that you'll see, right? If you can somehow separate the different frequencies of light spatially. If you can make the different frequencies go to different places, you can form the rainbow of light. So what I have right here is I have how the different colors are broken down by free space wavelength. It's easier, I think, to talk about free space wavelength than frequency, right? It's just easier to say, oh, 700 nanometers than whatever that is, 4 times 10 to the 14 hertz. So people usually talk about the free space wavelength when they're talking about the visible spectrum and the whole electromagnetic spectrum for that matter. All right, now these numbers right here, again, these are not hard edges. In fact, I got this from a particular source, another source might have the red going from slightly different values. So don't think the 622 and the 780 are sharp cutoffs. And in fact, my poorly drawn spectrum over here, this rainbow, that doesn't look like a true rainbow. Yeah, because I have hard edges between the different colors, and I also don't have any shading, right? So like a 780 red looks a little bit different to us than a 640 nanometer red. But this is the best I could do with my limited draw skills, so my drawing skills in PowerPoint. But there you go. Okay, so you should, quote, know the visible spectrum. You don't have to memorize all these different wavelengths, but you should know that if we go from long wavelength, the longest wavelength, which is the lowest frequency, that's going to be the red portion of the spectrum. So red is going to be the longest free space wavelength, and then it goes down in wavelength down to the violet. So if you look and list the colors of the visible rainbow, the different frequencies, the spectrum, from long free space wavelength to short free space wavelength, you're going to have red, orange, yellow, green, blue, violet. And you guys might be familiar, there's a mnemonic, Roy G. Biv. See? ROYGBV. Now, you may have been taught this in some physical science class, that there is an I to get Roy G. Biv, and I stands for indigo. That is not officially sanctioned in physics. There is no indigo portion of the spectrum. Okay, so that indigo was, if you see indigo, that was thrown in there just to give you the vowel, the I, to say Biv. But it's Roy G. Biv, right? There's no I there. Okay, one thing we can see with this crudely drawn spectrum is that the yellow band is very narrow. So your rods and cones, the photoreceptive cells on your retina, they only perceive a very narrow wavelength or frequency band to be yellow. There's also not a peak sensitivity to the colors, and we'll talk more about that when we talk about the eye. But your photoreceptor cells, their strongest response is right here, right near this yellow-green, right about I think about 570 or something like that nanometers. So that means, like, if I had a light that was a deep red, like 740 nanometers, and I had another light that was yellow, like right near this yellow-green, and both were putting out the same amount of energy per time, both were putting out the same power in their light wave, we would see the yellow-green to be much brighter than that deep red, because the photoreceptor cells peak. They have a peak sensitivity right here. And then it falls off as you go up in wavelength into the red. It also falls off pretty much at the same rate as you go down in wavelength into the deep violet. So it peaks right about here. But we'll see, again, we'll say more about that when we talk about the eye. Okay, let's see. Oh, this is just another chart that shows the electromagnetic spectrum in terms of wavelength and frequency that I put here. And I do have this exercise if you want to practice with. Now, again, I'm not going to test you over this exercise stuff because it involves calculations. But if you go to this exercise, let me just show you what you can do with it. Let me open it up. Oh boy. Did it open? Did it open? Let's see. Oh, sorry. Oh, I got to end my slideshow to see it. That's what I got to do. Let me just, here, I'll end the show now because we're not, this next slide is in the next video. let me just end this. Yeah, here it is. Here it is. So what you can do in this exercise, and again, don't feel like you have to, is if I give you some information, you should be able to figure out the rest of the information. Okay, now, so what you're considering is that these things are traveling in free space. Okay, so let me, right here it says free space. Oops, I just crossed it out, but it says free space. So what you're going to use is the fact is that the speed of light in free space, c, 3 times 10 to the 8 meters per second, can be written as the product of the free space wavelength and the frequency. Okay, so for instance, if I give you that the frequency of a wave in free space, a light wave, is 1 times 10 to the 14 hertz, you should be able to figure out the wavelength and then the type, where it is in the spectrum. So the way you would do that is you would say, okay, so the wavelength, if I solve that equation for lambda naught, should be c over f. All right, this equation, if I solve it for lambda naught. So then I'm going to put my values in there. 3 times 10 to the 14 hertz over 1 times 10 to, oh my gosh, I'm sorry. I am so sorry. My brain just merged these two. C is 3 times 10 to the 8 meters per second. I'm so sorry. And then I divide by 1 times 10 to the 14 hertz. There we go. Okay. Now, if you do this, remember the hertz is cycles per second. So the per second in the frequency in the denominator is going to cancel the per second upstairs in the speed. So I'm going to be left with meters. And you can punch this in your calculator, or you can use that shortcut for dividing scientific notation numbers. So this is going to be 3 times 10 to the minus 6 meters. 3 divided by 1 is 1, and then I subtract the exponents. Now, I could leave it like that, or I could remember that a micrometer or micron is a millionth of a meter, 10 to the minus 6 meters. So I could write this as 3 microns if I wanted to. Or you could leave it as 3 times 10 to the minus 6 meters. Now, where does that put us in the spectrum? And I think if I scroll down, I gave you the answers. I don't give you the spectrum. Oh, so that means is you have to go back and look at the spectrum. Here, let's go back and look at the spectrum. And where does that put us? Well, 3 microns, right? So 3 microns, I don't see microns here. I see centimeters, millimeters, nanometers. So let's convert this first to nanometers. So 3 microns. Now, a nanometer is 10 to the minus 9 meters. A micron is 10 to the minus 6. So that's a factor of 1,000. So that would be 3,000 nanometers. Okay. So 3,000 nanometers, let's see, this goes from a millimeter. How many nanometers is a millimeter, right? Well, a millimeter is 10 to the minus 3 meters. A nanometer is 10 to the minus 9. That means there's 1,000,000 nanometers in a millimeter. So a millimeter, that would be 1,000,000, 1 millimeter would be 1,000,000 nanometers. Okay, so this is 1,000,000 nanometers down to 780 nanometers. The 3,000 is in there. This must be infrared. Or a faster way to do it is 1 times 10 to the 14 hertz. That's going to be right in this frequency range. So if I go back to my Word document, I know that this is going to be infrared. Okay? And you could do the same thing for this frequency. Here I give you a wavelength, and you have to find the frequency and then put it in the appropriate part of the spectrum. Again, just do this if you're interested and want to have fun. You don't have to do this exercise. The answers are given right here. Okay, but again, you should remember the parts of the visible spectrum. Again, you don't have to memorize the visible spectrum, but you should know Roy G. Bove. Okay, so long wavelength to short wavelength goes Roy G. Bove, free space wavelength. Okay, that's it for this video. We'll talk about the index of refraction in the next video. Okay? All right, see you then. Bye-bye.